Hey y'all. So this is the last part of our Finsky-Underwood equation derivation. This time we'll just be focusing on Underwood equation and then plotting out what we derived on the whiteboard earlier onto Python. So for the part three, the last part is for we're asked for an equilibrium mix equimolar mixture of four components with the constant relative volatilities of 3, 2, 1, and zero point 0.5 respectively, with the light and heavy key volatilities of 2 and 1 respectively. Determine the minimum flux reflux ratio using the Underwood equations for a total molar flow rate of 100 moles per second and recoveries of 1.99, point 0.2, meaning point zero 0.02 and 0 in the distillated product for the four components. Okay. So, right as you see, for our libraries, NumPy and P, SciPy optimized for our because we had to use a root scalar for our Underwood equation. Um, and then make subplots. So for initial values, so as you said, for our we have equal molar mixture of four components. So for our mole fractions, we have 0.05. Um, for all for four components. So if we do these, I found this out. Uh, that you can just times by four and it'll display whatever your array four times. I mean your component four times in your array. So that's what our Z's is. So it's equal molar mixture for components. So our mole fractions be equal molar as well. So for components. And we have constant relativities, I mean relative volatility. So our alphas for 3, 2, 1, and zero point 0.5, and 2 and 1 being our light key and heavy key in this instance. And then our total molar flow our total feed molar flow rate is 100 moles per second. And then our recovery distillate, so our mole fractions for our recovery distillate is 1.99, point zero, 0.02, and then 0. Okay. So now let's start. I took the equation we have. I know this is more of a sloppier page that I usually have for my handwritten work. But this is what we'll do for today. We don't have to do a lot. So let's start. So first one to do is we want to describe this right here. So remember, we took our two equations that we got from Underwood, and then we combined them, and we got a equation for this. We got the Underwood equation for combining our stripping and rectifying stage for tire distillation column. So we want to actually define this first. So what we want to do, we have to find data. We already have our alpha and our z's because they were given to us, but we don't have data. So let's find our data. So let's define the function. So define our Underwood equation and then just define data. Just write the data. Okay. And all we're doing is that we want to return actually this the equation here. So what we were doing is that we do np.sum, so we're capturing the sum there. And then we are, oh, okay, I just want to make sure we're recording. I didn't know if I was recording or not. We do alpha times our z's, divided by alpha, minus theta. Oh, these are alphas. Okay. So yeah, shift enter. Now we have our theta. We have our Underwood. And now what we want to do, we want to actually put this into a root scalar. So we'll root scalar this. And what we do, all we do is we use one, put our function, so our Underwood, and then we don't need a lot anything else. We don't need an argument, our method. We do need brackets though to how much we're trying to scale this to. So we need parameters. And our parameters will actually be our light key and heavy key. So it'll be between our two and one for our light key and heavy key. Uh, but I know in class we didn't actually put two and one for our parameters. We actually put right in between it. So we don't want exactly to be one and two because it'll just go to zero. We don't want that. We want it to be like right before or right after one and two. So for one, we do 0.1. I know that worked in class. I mean, 1.01. You can go to one, you can do 1.e to like the negative 14 like we done other times, but I know in class we did this and it worked. So 1.1 and then we do 1.99. So right before we get to 2 and right after we got to 1. Okay. So we shift enter and boom, it converges and we get our root, which is what we need, what we want to find. We have our root for our Underwood equation now. Um, and we can really just dot root this and we can just call this, I'm going to say n. Actually, no, we're not. What can we say? Say lowercase r. Lowercase r. Lowercase r. That'll work. Because we're trying to find a reflux, but yeah, this will work. This will work. But we're trying to find our roots. So R for roots. Okay. So shift enter. And then we want to plot this out. So you can see actually how this is done. How it will look on a how this will actually look visually. So we just do theta plot, which would be our x's. Then we do NP line space, NP lens space. And then we want to have it from our alphas. So we do 0.4 to 3.1. So right after right before and after our the range of alphas. And then we do 200 points. Okay. And then our Y would just be our Underwood values, which in this case would just be NP dot array of our Underwood equation. Oh, yeah, this would be bracketed up. Our Underwood equation. And then to theta. And then we will also do, remember, we want to loop this uh as many times. We want to loop this for as many times as theta. Well, as many times for theta plot. So what we would do, oh, we did this actually in the distillation column, if you remember. Well, when we had to loop our array, the inside our array, same thing. So for theta in theta plot. So loop as many times we're going for our theta plot. So this will be continually looped. Yeah, that's pretty much it. We can just plot this now. So fig that makes subplots. You're gonna make subplots. You want to add scatter. So fig dot add scatter. Um, this is equal to our x being our data plot. If I can spell. There we go. Data plot. Our y equaling our underweight values. And then fig dot update layout because I don't want to get blinded. Oh yeah, this doesn't have to be equal to. What am I doing? There we go. Height equal to, let's say, 600. Width she got 500. Uh, and then template, of course, our trusty poly dark. Okay, should enter. I spell it wrong. Add scatter. What's wrong? Said to be equal to? It may as be equal. You know what? I'm pretty sure there's no equal. Yeah, there's no equal. Add scatter. Fig dot add scatter. Why does it not work? What the heck? Oh, it's because I forgot mine. Okay, there we go. There we go. I was like, why is it not working? I forgot to put my parentheses. It's my mistake. Now let me actually change the bound to this. Make it a little bit. Let's switch these 600 and 500. So yeah, here's our plot. I'll zoom in on this. But as you see here, this is basically representing our roots for our underwood equation every time we see our line go over the z, I mean, our zero value, that is us collecting our root for the stage. Um, so yeah, um, that's basically it. So as you see, we have four roots. Our fourth one may be imaginary in this case, but these three roots here are our three roots for our function. But yeah, okay. So next, the last part is that we want to actually find our reflux. So we want to actually use this equation we found earlier on the whiteboard. So what we'll do, we actually already have everything. Now we just gotta put it into the equation. So we want to use our rectifying stage equation for this. But I do want to note that what we'll be using for our distillation, our distillate, we'll be using the total flow rates. Um, so we're using our F total instead of our distillate. We'll circle back around to that later. Um, like we'll find we'll circle back around to it later. Okay. Because we're giving the total flow rate, and then we're getting our mole fractions for our flow rate, our total flow rate. So we'll use the total flow rate for now, and then we'll use our rectifying our mole fractions for our distillate to then find our distillate for our reflux. Okay. Let's start. What are we doing? We need to find uh our flow rate, our molar fraction for our feed. So ZF. So now this be equal to our Z's um times our total feed, molar forward oh I can't talk. Our feed molar flow rate. Okay. I don't know why it sounded like a ton that was a tongue twister. Jeez. Okay. So we have our molar fractions for our feed. Now we can actually use our find our rectifying stage equation for our volume. So our volume is equal to our NP sum of our uh so we start with our rectifying distillate. So our distillate molar flow rates times our ZF, and then times our alphas. And then this would be all divided by um our alphas again, and then minus R. Because in this case, remember we defined our R as this is our theta. Remember, this is our theta. But we can't really use our theta right now. Well, we're using our theta, but we have it represented as R up here. So we're just come back here and represent this as R down here for our theta. So we shift enter that. We have our volume now for our rectifying stage. And now we replug our volume in for our reflux. So we know that our reflux is equal to our volume. And then this will be divided by, and then this will NP dot sum. So this is what I was talking about. We will use our total feed, and then we'll use from the feed, circle back around to find our distillate. So this will just be what is it? We can find our distillate by using our molar fraction times our recovery of the distillate. And this would be also times our feed. Okay. So that would actually equal out. That'll give us our distillate, and then we get to subtract this by one. Or so minus one. So this should be right. Oh, I'm in feed total. Oh, there you go. Oh yeah, that should be good. So let's see what our reflex is. Okay, that's not right. Is it because I added this? Let me see. It is. Okay, so what actually all we have to do, I'm sorry, it's because we actually already did this multiplication of our V total times our Z's. So we don't have to do it again. This is just a representation of that. So of our mole fraction times our feed. So since we already have that, so it's our mole fraction times our feed times our rectifying, our mole fraction of rectifying of our distillate, mole fraction of our distillate. So now since we already have this equation, we know that this equation does equal to our distillate mole flow rate. So we can this will equal out to our distillate mole flow rate, which we then divide by we it will work for the equation and we subtract by one. So this is our reflux. This is our minimum reflux that we can get for our distillation column with our current constraints. Um, yeah, that's it. It's pretty simple, not too complicated. But yeah, we found our minimum reflux. Okay, uh, that's it for our Underwood equations and derivations. Hopefully this helped you guys out, and I'll see you guys in the next video. Bye.